This is my Physics 2211 Lab 5. So the purpose of this lab is to determine what forces are acting on a slinky and the y position change when it is held from a distance. A synopsis of the conclusion is that the tension force holds the bottom up while the gravity forces the top down. So the models and physics principles in this are Newton's second law of momentum, position and velocity update, the drag formula, model experimental data using the tracker application, as well as model computational data using coding and simulations. And this was all used to track the y position change. So the position and velocity update formulas are shown, and they were used to extract values from the raw data to be inserted to the computational model. Newton's second law is momentum equals mass times velocity, which relates to force equals mass times acceleration, and these were used to see the acceleration in the y direction, as well as the drag formula to account for air resistance. So the system was the slinky, and the surroundings were the air and ground. A slinky is held, and the initial conditions is that the slinky is held from a distance and then released. In the coding, the initial conditions was that the ball weighed 0.25 kilograms. This is the initial position and velocity vector. The delta t was 0.33 seconds. The gravity is, or constant is 9.8, and then b equals 2.6, which goes to the drag equation. And this is the tracker data. So the tracker data is slowed, so it shows a extended version of what the data should be as well, and it is shown here. We're looking at the y data graph, and around like 5.5 seconds into the video, the slinky starts moving, and this will be reflected in the code in a shorter time sequence to simulate real life. This is the code. On the left side, this is all the components of the visualization that is put into seeing the graph. And on the right is on line 73 to 74. First is the gravity, force of gravity, and the second is the force of drag, which are added together and put into the position and velocity update formulas in line 78 and 79. And this is the visualization of the force, and the graph is shown here as in a shorter time interval. As you can see, on the tracker data and in this data, there is a plateau reflecting real life. So some conclusions. The graph looks very similar to simulation data. The differences is that the time in which the y position of the slinky changes is different. And this is because the original tracker data was slowed down in order to collect all the data points, while the coding was used to reflect how normal gravity and time works. Some errors that have gone into this is coding and tracking errors. Coding includes like just using the wrong numbers, or just in case there have been incorrect calculations in the equations. And then tracking would just be clicking the wrong point in which the slinky is moving. There may have been also incorrect drag constant, as well as forces that have not been accounted for, such as spring energy in this. So the graph shows a general plateau, then a drop for the y position, and the equations used was drag, gravity, position, velocity update. And the conclusion is that the reason why there's a drop is because the force of gravity pushes the top downward, while tension keeps the bottom still until it compresses and gravity force overwhelms tension and the entire slinky goes down to the ground. So again, the what does it mean question, the question that I chose is that the tension force keeps the bottom of the slinky in place, while the gravitational force on the top of the slinky downward. When both collide, the gravitational force pushes the whole slinky down. And so for the what if question, what if the slinky is treated like a spring in the code, the values may have been more accurate to the real y position change of the slinky. Thank you.